Hi, my name's John Broadwell, and I'm an independent embedded systems consultant, as well as the creator of the Serial Wombat open source project. Today we're going to be talking about software testing of the Serial Wombat, and I'm going to show you what I do to assure the software quality of the Serial Wombat 4B firmware. To me, any piece of software that's good has to have associated automated testing with it. And so I'm going to show you a circuit that I built that lets 3 Serial Wombat chips test each other while being commanded by an Arduino unit test program that I wrote. We'll go through the circuit board and we'll take a look at the Serial Wombat Arduino library example that's available in the library that you downloaded, and we'll see how that works, and we'll run it against a few different boards. We'll be looking at the Arduino Uno. We'll be looking at an ESP32 node MCU type board. We'll look at one of the microchip SAM21 based Arduino Shows, and we'll look at an ESP32 board and assure that the Serial Wombat Arduino library runs properly on each of them by running the same set of tests. Shown here is the initial version of the circuit I created in order to unit test the Serial Wombat firmware in the Arduino library. You can see that there's 3 separate Serial Wombats on 3 different I2C addresses, 6C, 6D, and 6E. We've got a couple of pull-up resistors, and we've got lines that come off of the breadboard for power, ground, I2C clock, and I2C data. Here you can see a number of 1K resistors. Each of those resistors ties the pin of one Serial Wombat to the pin of another Serial Wombat. And by having one Serial Wombat generate pulses and another Serial Wombat measure them, we can check to make sure things are operating properly. For instance, we might have one Serial Wombat generate servo pulses and a second Serial Wombat use its pulse measurement capability to verify that the pulses generated by the first Serial Wombat are correct. Let's take a look at the schematic. The schematic here shows the layout of the PCB board created for unit testing. We have a header on one side that allows us to input 5 volts, which is the voltage which is fed to the 3 Serial Wombat chips. 3.3 volts, which is fed to an optional OLED that can be attached. That 3.3 volts is also the voltage that is fed to the SDA and SCL 2.2K pull-up resistors for the I2C bus. Note that there's no reason why you couldn't connect 3.3 volts to both of these if you were connecting to a 3.3 volt system as well. Ground, and then the data and clock lines that come from the Arduino. There are 3 Serial Wombats, each of which has power, ground, and the appropriate decoupling capacitor, clock, and data lines for the I2C. And then each Serial Wombat connects to a pin on a different Serial Wombat. So for instance, WP0, which is an input 0 pin, is also connected to WP2 on a different Wombat. C2 on the 6E Wombat is connected up to WP2 on the 6C Wombat. So they basically have a crisscross configuration. On the PCB board, I got rid of the resistors, the exception being 2 unused pins over here. I connected them with a resistor that would allow me a place to solder things on or to otherwise measure things. It just, I don't know, it felt like the right thing to do with a couple of pins I didn't need. I could also have, I suppose, pulled them out to through holes, but I didn't. You'll also notice this set of 3 switches that allow the addition of an RC filter on D3, D2, and D1. And what that does is it allows us to drive a PWM on C1 that will then get filtered into an analog voltage on D3, D2, and D1. And that's how we test in an automated way our analog inputs, is by driving a PWM that then gets filtered. And we look to say, okay, is that approximately correct on the analog inputs if we drive it at a sufficiently high frequency that we get good filtering. There's also a 10-pin connector down here which is designed to allow connection of a logic analyzer. Now let's take a very brief look through the Arduino example that's available under File, Examples, Serial Wombat if you've downloaded the library. You can see we declare 3 serial wombats. There's a variety of things that I do here to make the other code easier later on, where we say, okay, what serial wombat matches up with what pins. It assumes that there's 4 pins. We declare various pin modes. The serial wombat goes through a reset on each one. We do some setup. We check the version number of each one, and we lock up and give an error message if for some reason we don't get a response. One thing to note is that there are functions that are called by each test for pass or fail. Inside of fail, there is the option to set a digital write so that you can wiggle a pin high and low. That would be useful if you wanted to trigger a logic analyzer on a failure specifically so that you could capture that failure. For instance, if you were looking at a servo and you got a pulse measurement that wasn't what it was supposed to be, you could take a look on the logic analyzer and see what happened. Those are commented out because the digital pins tend to vary from platform to platform, but if you need them, you can comment those back in. Other than that, there's a variety of different tabs, each of which runs a different functionality or pin mode, and you guys can kind of just wander through those and take a look. But the important thing is that you can go to Sketch, Upload. We'll open up our serial monitor here, and we can see it starts running the test. It verified the Serial Wombat versions. It ran a digital I/O test. That one was a quick one. They all passed. It checked the supply voltage. That passed. Now it's running an echo test, which just sends random data packets to the Serial Wombats and makes sure that they respond the same packet back. That's good for checking the quality of your I2C connection. After a few minutes, we see that it completes the servo test. Out of that test, it ran about 89,000 permutations of different pins and different pulse widths and reversals and all of the various interfaces. And out of those, we had 2 that failed, where it got a different measurement than what it expected. I haven't been able to totally track down why we get these very rare failures. My guess is that it has something to do with a transition followed by a very rapid measurement where we don't get the expected value. But I will continue in the future to keep an eye on this. But at this point, 2 failures out of 90,000 tests are what I would consider to be acceptable. The failures don't consistently happen on the same measurements. Right now, the PWM test is running. Let's take a look at that on the logic analyzer and see what's going on. Here we can see we're testing a PWM on one of the pins. You can see the SCL and SDA I2C data lines going back and forth. We're changing. You can see the PWM progressively getting longer. We're essentially cycling through different duty cycles on that PWM. And then when it gets to the end of that one, it'll move on to another. I'll pause for a second, and then we'll take a look at that. You can see here now we moved on to a different channel. And if we were to watch this for 15 minutes straight, what we would find is that it's also cycling through various frequencies as well. So this is just a short look at how I do the unit testing. The entire unit testing sequence takes quite a long time because of the number of iterations of different interfaces that we test. But the end effect is that I feel really confident when I make changes to either the Arduino library or the firmware library, the embedded firmware, and I rerun these tests, that we only make things better. We don't make things worse. So if you have any questions, please leave me a comment down below. I'd highly suggest that you subscribe to this channel if you're interested in the Serial Wombat, because this is one of the best ways for you to get push new information for our new firmware releases or Arduino releases or updates in other platforms. We're also going to have a couple of new chips that will be added to the product line in the future, and so you'll be able to find out about those. Thanks for your time. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features to the Serial Wombat. The Serial Wombat open source project was created by Broadwell Consulting Inc. Broadwell Consulting Inc. provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Questions sent to John at Broadwell Consulting about the Serial Wombat will not be returned.